Good morning, everyone. My name is Dick Yeomans with David H. Paul Incorporated, and we are here today to talk about power generation water treatment. Um, Today's webinar should last roughly about an hour, somewhere between 30 and 40 minutes of the presentation that I'm about to go through, and then we will have 20 minutes or so of questions and answers. Um, Now, there is a text box on your screen where you can type your questions into, and your questions will not be answered immediately. They will be answered at the end of the entire, I don't know, 30, 40-minute presentation that I'm going to make, but we will address the questions at the end. If I don't have time to get to all the questions, we will cut it off at about an hour, and then I will address each additional question in an email to you at a later date. So that's the plans for this webinar. We are going to record this presentation. It will be available later on our website at dhptraining.com /recordings, where you could either review it later or have one of your associates take a look at it. And at the end, within the next day or so, you will be sent a thank you email and a PDF of this presentation for your reference and review. So we're going to get started today. The agenda is going to be, we're going to talk a little bit about my experience, and then we're going to get right into power generation water treatment. So, Dick Yeomans, to introduce myself, I've been working in the industrial water treatment industry for over 35 years now. I graduated from the University of Georgia with a BBA, Bachelor of Business Administration, in 1973. I did complete a David H. Paul program through San Juan College in 2002, so I do have an associate degree in Applied Sciences of Water Treatment from David H. Paul Incorporated back in 2002. I worked for Buckman Laboratories for almost 20 years in a lot of different positions, but the most important was I was their RO product line manager, and that's where I met David back in 1998, and basically took all of David's training programs back then. I even got, after I finished my associate degree from San Juan College, I actually was certified and licensed by David to do several of his training programs around the world for all of Buckman's customers and actually their salespeople also. So I did develop Buckman's product line for RO treatment, and then as it worked out, after all those years, I started working with David, DHP, back in August of 2013. So I've been involved in the water treatment industry a long time, and specifically reverse osmosis, since the late 90s. Let's say 1998 would be a good time period for that. So that's Dick Yeomans in a nutshell. What we want to talk about today is high purity and specifically power generation water treatment. So any good design engineer, water treatment person, or consultant, one of the initial things he's going to want to know when he enters your facility is, what is your raw water source and what are your end-use specifications? Those are very clear parameters that have to be understood, because what goes on between those two things is what we're going to call a water treatment scheme, and that's what water treatment is. Taking that raw water source and conditioning it, if you want to put it that way, to meet those end-use specifications. So let's take a look at raw water sources. This is pretty simplistic, but we have surface waters and we have ground waters. Surface waters, very simple. Lakes, rivers, oceans, they're all on the surface of the Earth's surface. And since they're on the surface, those water sources change on a regular basis, and they can even change on a daily basis, on an hourly basis. Things like the temperature. Obviously, if you're in a climate with the temperature swings, like in the northern United States, from what 80, 90, and maybe even 100 in the summers, all the way down into below freezing in the winters, your temperature is going to change. That's going to affect the operations of your water treatment plant. Anytime there's rainfall, there's always a lot of runoff. I live on a farm, and every time the wind blows, my pool gets full of debris. So surface waters are always subject to change because of the suspended solids in the air. Sunlight obviously affects the growth of microorganisms, especially algae. Once again, go back to the temperature and the seasons of the year, and then that runoff after rain, and there's some other things that affect it. But surface waters in general are very high in dissolved oxygen because they're in surface with the atmosphere, in contact with the atmosphere. They're also extremely high on TOC. TOC is basically the breakdown products of both plant and human waste, or for that matter, all animal waste. They're also very high in non-living particles, meaning they're also going to be very high in living particles, meaning microorganisms. They're generally going to be very low in TDS unless you're dealing with a bay water or a seawater, which means they're going to be low in conductivity, silica, and dissolved CO2. So surface waters have their own characteristics. They are going to change on a regular basis, like I said, maybe even hourly. That needs to be understood by your water treatment people and your water treatment scheme in your facility. Now that's as opposed to well water sources. And when we're talking well water, we differentiate them into two different categories, meaning superficial and deep well waters. Superficial is very shallow well waters, and since they're shallow, and I'm not going to put an exact number to that, I don't know, I don't think anybody ever has, but that means that they're so shallow that they're still under the influence of that surface water, or for that matter, a rainwater could even percolate down and affect a shallow well. So they're going to be variable also. So that needs to be taken into account when you're developing your water treatment scheme. Now, deep well waters are a different story. They're fairly, and you might even say extremely stable. They can change, but it's going to be very slowly over a long period of time because they percolated down through the Earth's crust, and they're going to be deep down in the aquifer. Their characteristics, as opposed to surface water, they're going to be very low in dissolved oxygen and TOC. They're going to be low in non-living particles and low in living particles. Now, the exception to that is that these deep groundwaters, since they're low in dissolved oxygen, might even be very, very low in dissolved oxygen. They could promote the growth of anaerobic bacteria, which is bacteria that don't like oxygen. They can't live in an oxygen atmosphere. So the lower the dissolved oxygen, the more the potential for those anaerobic bacteria to proliferate. And more often than not, it's the species, some type of species involved with iron-related bacteria. They will be very high in TDS because they've percolated down through the Earth's crust, and we all know that water is the universal solvent. It will dissolve anything it ever comes in contact with. So the longer or the deeper it percolates down through the Earth's crust, the TDS and conductivity is going to be higher. We all know that the Earth's crust is one of the major constituents of silica, so they're going to be much higher in silica and obviously a lot higher in dissolved CO2. So there's a lot of difference between groundwaters and surface waters, and that needs to be taken into account developing your water treatment scheme depending on your water source. Well, the other half of the equation, now that we totally understand your water source, is your end-use quality. In other words, anything that's not pure water, pure H2O, is considered a contaminant. And your end-use specifications are going to dictate what type of treatment scheme we need to remove what we're going to call contaminants. Once again, anything that's not pure water is a contaminant. So we're going to take a look at a couple of end-use specifications real quickly. And since we're talking power generation, we're going to start out by talking about the fact that it's very obvious. The higher the boiler pressure, the higher the temperature of the boiler water is going to be. So the higher the temperature and pressure, we're going to need purer or better quality feed water going to that boiler. So here's just some very quick, and this is very quick, water quality parameters for different pressure boilers. And you can see I picked out two that are pretty wide range. One boiler between basically 0 to 300 psi. You can see the dissolved oxygen, iron, and TOC levels that are allowed. However, look at the difference when you get up into the higher pressure boilers. And in this case, those are pretty high pressure boilers, 1500 to 2000 psi. You can see the dramatic decrease in the contaminants that we can allow into that boiler to prevent corrosion and or deposition, which would cause underdeposit corrosion in those different systems. So it's critical for those things to be totally understood walking into any design phase of a water treatment system. So now that we've talked about the water sources and the end-use parameters, so to speak, let's talk about high purity water treatment itself. And by high purity, we're getting into that power generation water treatment, because we're getting into those higher pressure boilers, which means we need better quality, higher purity boiler feed water going to those boilers. So if we take a look at a typical water treatment scheme, we talked earlier about raw water versus end-use water. Well, we're going to throw an RO unit in there. And the only reason to have an RO unit in your water treatment scheme is for TDS removal. And it does. It removes the bulk of the TDS, the total dissolved solids, all that stuff that contributes conductivity. That's what the RO unit is doing. That's its purpose. Well, that raw water is not good enough to feed into an RO unit, so we're going to need something called pretreatment. Our pretreatment scheme is there for one reason only, and that is to protect that RO unit. If we're not protecting that RO unit, anything that happens downstream is going to be horrific. So we need to develop a pretreatment scheme, taking that raw water, making it good enough for us to feed into an RO unit. Well, at that point, that RO permeate is not good enough for our end-use specifications. So we're going to need another treatment scheme. It's called post-treatment. The purpose for post-treatment is to take that RO permeate and polish it. And in other words, make it better for those end-use specifications. And everybody has different end-use specifications. And we're going to take a look at some of those later when we start talking about internal boiler water treatment. But every different facility has a different end-use specification, and that's all post-treatment does, is takes that RO permeate, and it might even be another RO unit. It could be a variation of different treatment schemes, some of which we're going to talk about in the upcoming slides. But that's all post-treatment is doing, is polishing that permeate to meet our end-use specification. So speaking of an RO unit, let's take a look at an RO unit. The way an RO unit works is we have a feed water entering the RO unit, and we manufacture, if you want to put it that way, permeate. Permeate is forced through the membrane by pressure. Now, in subsequent slides or training programs, we're going to define that pressure as net driving pressure. But for right now, all we want to understand is that pressure is what forces water through the membrane. That's what forces our permeate through the membrane. We also want to understand that salt passage, salts, dissolved solids, TDS, they get through the membrane by diffusion only. Dissolved solids going through the membrane have absolutely nothing to do with pressure. So you just found out the first reason you have a post-flush rinse a post shutdown rinse when you turn off your RO unit to get that concentrated water out of there. So diffusion is going to happen regardless of what's going on pressure-wise, whether you have your high pressure pump on or your high pressure pump off. It's the same thing if you take a teaspoon of sugar and put it in a glass of water or a glass of tea and you don't stir it, the sugar is going to settle to the bottom. Well, by what we call random motion and diffusion, over time, those dissolved solids are going to spread out into that solution of iced tea or water, and you have a very uniform distribution of the dissolved solids. Same thing happens in an RO unit. And you'll notice in the picture that I've got up right now, at the beginning of the RO unit, and I should have mentioned this is the universal symbol for an RO unit or an RO element, where we have a feed water going in, traveling across the surface of the membrane, which is the diagonal line. And you'll notice that at the very beginning we got a little bit, we got one dot up there for diffusion. But as we move down, we've got 2 dots and then finally 3. Well, I'm going to describe what's going on right there by telling you, you just learned the second thing about diffusion. The higher the concentration of the feed water, the higher the rate of diffusion. So as the feed water travels down or through the membrane unit, we're making theoretically very pure permeate. So all those dissolved solids in the feed water are concentrated. So the feed water is concentrating all the way through the RO unit, and the higher the TDS of the feed water, the higher the rate of diffusion. So that's why you make your best permeate in an RO unit, first inch, first element. You make your, I hate to say worst quality, but your highest TDS permeate, last inch, last element, because of the concentration factor. So you put the two together, you put water passage and salt passage together, and I love this phrase. This is how an RO unit works. A whole lot of dilution, a little bit of diffusion. Water is forced through the membrane by pressure, which is the whole lot of dilution, and then dissolved solids diffuse through the membrane, and that's our little bit of diffusion. So that's how an RO unit works. One of the important things we mentioned earlier about surface waters is temperature. The warmer the water, the more fluid it is. It has a viscosity, just like motor oil. 50-degree motor oil is very viscous. It's thick. It doesn't flow very well. But you heat it up to 90 degrees, and it flows very well. So water has a viscosity just like that. The higher the temperature of the water, the lower the viscosity, which means we need less pressure. And I defined that earlier as net driving pressure, but it takes less pressure to produce the same amount of permeate. Here's the third thing you're going to learn about diffusion, and it's temperature. The higher the temperature of the feed water, the higher the rate of diffusion. So the higher the TDS is going to be in your permeate. So if you're on a surface water source, once again, we can expect in the summer the TDS of your permeate is going to be higher than it's going to be in the winter because of that temperature effect on the rate of diffusion. So that's how your RO unit works. But let's look at the flat sheet piece of membrane. How does it work? Here's how it works. There are 2 categories. Let's go back. Dissolved and suspended. Well, let's talk about those charged dissolved ions. How are they rejected? It's very simple. The higher the charge, the higher the rejection. Now you're looking at that going, okay, sodium +1, chloride -1, 99% rejected. Well, what's the difference in calcium +2, carbonate -2, sulfate -2, 99.5%? You're looking at me going, Dick, this is ridiculous, but that's how the membrane works. The higher the charge, whether it's positive or negative, the higher the charge, the better the rejection. How about those uncharged dissolved ions, like sugar, those organics, all those things that are not charged in water? How are they rejected? Well, they're rejected based on molecular weight. The higher the molecular weight, the better the rejection. So you can see molecular weight of water, H2O, hydrogen weighs 1. There's 2 of them, that's 2. Oxygen weighs 16. 2 plus 16 is 18. Molecular weight of water is 18. It's not rejected at all. It's forced through the membrane. But the higher the molecular weight of that uncharged dissolved substance, shows a very good example, the better the rejection. Anything over a molecular weight of 200 is 99.99% rejected. And then right above that, you can see gases. Gases are not rejected whatsoever. And that comes into a lot of play later on when we're going to talk about degasification. Gases go straight through the membrane. They are not rejected whatsoever. And then we don't really need to even discuss suspended solids, whether they're living or non-living. Living, a good example of living would be microorganisms. They're all basically between half a micron and maybe 1 micron in size. And then the non-living guys, which would include sand, silt, clay, or dead microorganisms. So the membrane is a barrier layer with a pore size of 0.0001 microns. So suspended solids are basically not going to pass through the membrane whatsoever. They're nearly 100% rejected. The only way they get through the membrane is by O-ring leaks or membrane damage. So, potential problems that all RO units face. Well, before we talk about the potential problems, we've got to understand that that downstream stuff we were talking about, that post-treatment, it's only going to work as well as your RO unit's working. If your RO unit is not working well, your post-treatment's not going to work well. So good performance of that RO unit is critical. And guess what that depends on? It depends on controlling 3 very important potential problems that all RO units face. Those 3 potential problems are scaling, fouling, and chemical attack. So that's why we have pre-treatment to protect our RO unit. If we're not protecting our RO unit, our downstream post-treatment equipment is not going to operate very well. So let's take a look. Scaling. Scaling is very simple. It's the precipitation of those dissolved solids in that feed water source. We're concentrating that feed water all the way through the RO unit, and at a certain point, those dissolved solids, that TDS, is going to concentrate up, and something's going to reach its saturation limit. Once it gets over 100% saturating, it's going to precipitate out as scale. So anything, whether it's calcium sulfate, calcium carbonate, barium sulfate, barium strontium, magnesium silicate, anything that goes over 100% saturated in that feed water is going to precipitate out as a scaling in the RO unit. Fouling. Well, that's where we're going to have something plugging the feed water spacer or actually plating out on the surface of the membrane. And that very well could be something like a sticky polymeric precipitate. And we're going to see some of those in a minute, but an overfeed of polymers from the city, the cationic coagulant, the anionic flocculant or cationic flocculant, then your anionic scale inhibitor, if you're feeding all of those guys, overfeeding them, they don't play together very well. They make a sticky polymeric substance. And fouling is the biggest problem in the RO industry, by far, by far. And you can even go so far as to say biofouling is the largest potential problem any RO unit will ever face. So that fouling problem is controlled by 2 things, flux rate and the cross flow rate. Well, flux rate we will also define as water flux, and we define that as the amount of permeate being produced. And we're going to go much further than that and define that as the amount of permeate produced per square foot of membrane surface area per day. So water flux is critical. The more water you're pushing through each square foot of membrane surface area, you're pushing stuff down on the surface of the membrane. All those dissolved solids, all those suspended solids, all those microorganisms, all those colloids that got into the RO unit. Colloids are anything less than 1 micron. So yeah, they're going to get past my 5-micron cartridge filter. So all this stuff is being pushed down on the surface of the membrane. So the more water I push through each square foot, the higher my fouling rate. The other half of that equation is cross flow, and that's the gallons per minute of the feed water / concentrate flow rate. The higher that flow rate is, the more we're washing that stuff off the surface of the membrane that's being pushed down there. So those two things work hand in hand. It's like juggling. The clown that's juggling those balls up in the air. You've got to juggle water flux because you want to make more permeate, but you also have to take into consideration your cross flow rate, because the more water you push through the membrane, the less your cross flow rate is. So you got to juggle those two things to determine your fouling potential in an RO unit. Here's two pictures of typical membrane fouling. One on your left is organic or colloidal fouling that's been, like I said, stuff is being pushed down on the surface of the membrane. So we're actually coating, we're putting a coating down on the membrane surface. Or on the right, the sticky polymeric. Now that could be a reaction between those polymers I mentioned earlier, or it could be microbiological. It's hard to say. I would probably guess microbiological in this case because of the blackish color around the edges. But that's what the sticky polymeric or biological fouling can do to the feed water spacer. So we got two things to worry about fouling: membrane surface and the feed water spacer. What are the things that do that? Bacteria, microbiological activity. Hey, the things that aren't supposed to be there, silt, sand, clay, we're supposed to be getting those out of there. They should not be entering the RO unit. RO unit is a fantastic, that RO element is a fantastic filter. Our cartridge filter or our filtration systems in front of it are good filters. If we let things get into the RO unit that shouldn't be going in, that great filter is going to filter them out and it's going to foul. Rust and precipitates. Dissolved iron is no problem in an RO unit. Dissolved iron is no problem. But when it's oxidized, whether by chlorine or actually even air leakage into your high pressure pump, you can oxidize dissolved iron, and all of a sudden it's a rust particle or it's a precipitant, and it will foul your RO unit. Obviously, we don't want oils going in, hydrocarbons. Now we get back to that cationic flocculant polymers the city might be adding. They're cationic coagulants, and then you're adding an anionic scale inhibitor. Those things don't play together well if they're overfed. They form, for lack of a better term, glue or sticky polymerics that's going to cause fouling. Chemical attack. What causes chemical attack? Well, chemical attack is when something oxidizes the surface of the membrane, and it actually burns a hole in the membrane. So you get a reduction in salt rejection. In other words, more salts are going to pass through the membrane because now you've oxidized it, you've got a hole in the membrane. Here's an example of what we do during an autopsy, and it has to be during an autopsy because we're sacrificing the element. But we cut out 3 swaths, one at the feed water end, one in the middle end of the element, and one at the end of the element. We put them in pressurized blocks, and we send a feed water across the surface of the blocks. While the feed water is circulation through the blocks, we inject a high molecular weight dye. Keyword, high molecular weight. Remember back in the first section we talked about how things were rejected by the membrane. One of them is high molecular weight. So the dye should be on this side of the membrane. But after we circulate it for a period of time, we depressurize, we pull the swaths out, and we turn them over. And we look at the permeate side. Permeate side should be clear. This is indicative of chemical attack. As opposed to the same procedure, and we pull the swaths out, flip them over, and now we can actually see where the feed water spacer was sitting on the feed water side. In between the crosshatches of every one of those little fibers, we've had chemical attack. So chemical attack, what causes it? Normally, I'd say probably high 90% of the time it's usually chlorine. But any oxidizer will do it. Scary part here is hydrogen peroxide and peracetic acid are actually approved for chemical cleaning procedures in places like semiconductor or water for injection plants. where they need extremely low pathogen permeate. They'll actually sanitize their RO units on a regular basis with these two guys, knowing the entire time that they're slowly but surely oxidizing the surface of that membrane. So they have to be very careful when using these two reagents for chemical cleaning. Okay, so we talked about those three potential problems. Well, what do we have in the system to protect us from that kind of stuff? We do know that if we have poor RO performance, we're going to have poor post-treatment performance. So that performance of that RO unit depends on the performance of our pretreatment equipment. So that pretreatment is there for one reason, to protect us from those three potential problems. We talked about them earlier. The three problems are scaling, fouling, and chemical attack. That's what RO pretreatment is for. So let's take a look at scaling control. There are three methods. We can feed acid. Acid does one thing. It lowers the pH of the feed water, and what it does is it changes there are three forms of alkalinity, carbonate alkalinity in any water source. CO2 reacts with water that's carbonic acid at the lower pHs. When you get up into the neutral pHs, it turns to bicarbonate, and then the higher pHs, it turns into carbonate. Well, if we can feed acid to lower that pH, we can keep that carbonate down into the bicarbonate and probably down into the CO2 or carbonic acid stage, so we can't scale. We can't have calcium carbonate scale. Acid is only effective for calcium carbonate scale. We can feed a scale inhibitor. Scale inhibitors are fantastic. They can increase the solubility. Remember that 100% saturation? They can increase that 100% saturation on all scales up to a limited amount. Scale inhibitors are fantastic. You have to have the right blend of scale inhibitor, and you have to feed the right amount. But if you do that, right blend, right amount, you can pretty well take care of most scaling species. And then last but not least is an ion exchange technology. We'll mention a little bit in a later slide, but softening. If we take the hardness ions out, it's an ion exchange. We're taking the calcium, the magnesiums, the bariums, the strontium, and exchanging them on an ion exchange resin bead for sodium. Sodium is our friend. It's a +1 charge. It's non-scaling. If we take out those +2 charge things, the barium, the strontium, the calcium, we can't have scaling other than silica. So those are the three technologies to control scale. Fouling control. We got to get rid of those particles, those things that create the fouling. So we use filtration technologies to do that. Media filtration. If we go through a multimedia filter or a sand filter, we can filter down to around 10 to 15 microns with media filtration. Cartridge filtration. Yes, we can get all the way down to 1 micron. There is a 1 micron absolute cartridge filter. So we could filter all the way down to get all those suspended solids out with a cartridge filter. Typical cartridge filtration in front of an RO unit, usually 1 to 5, maybe even a 10, but 1 to 5 is more prevalent. And then finally, membrane filtration, microfiltration and ultrafiltration. That's one of the waves of the future, especially in the larger plants. Membrane filtration consists of microfiltration and ultrafiltration. Microfiltration, the pore size is 0.01. Ultrafiltration, the pore size is 0.001. And then finally, the third problem we have is chemical attack control, which is the removal of oxidizing agents. Remember that chlorine compound? If we can get rid of chlorine in the feed water, we can protect our RO unit, our RO elements from chemical attack. 3 ways. Activated carbon. Activated carbon will dechlorinate a feed water source. We can also inject sodium sulfite, sodium metabisulfite, or sodium bisulfite. The sulfite is the key factor here. Sulfite reacts with oxygen and with chlorine, and then dechlorinates the water source. Or we can use UV light. Trouble with UV light is it takes a whole lot of intensity. So very rarely will you see UV light for dechlorination, but it's a technology that is out there and is available and is used in some circumstances. So that pulls us full circle. We've talked about the raw water and the pre-treatment that's needed to protect that RO unit. Now we're going to start looking at some of the post-treatment things that we're going to take that permeate and polish it up for the end-use specifications. So here's where we are. Meeting high purity water treatment specs. High purity meaning we're in a power plant, power generation. The higher the pressure of that boiler, the purer water source we need going in that, the better feed water source. So good post-treatment performance goes back to our good RO performance. Good RO performance goes back to good pre-treatment performance. So what are some of the technologies used to polish? They are ion exchange. And once again, just like that softener I mentioned earlier, ion exchange removes the remaining ions in the RO permeate and also reduces the organics. So what we're doing is we're exchanging undesirable ions for desirable ions, meaning we're taking any calcium, magnesium, for that matter sodium, anything, any cation that's remains in the water, we're going to exchange it for hydrogen. Any anion that's left in the permeate, we're going to exchange for hydroxide. So the combination of those two will form water. So our ion exchange is going to help us better purify the water going to downstream applications. Here they are. We can do softening like we did in front of the boiler. We could have dual beds, which is an anticationic resin in different beds, or we can use a mixed bed technology, which is pretty prevalent downstream on the RO unit. Is mixed bed where we have both cation and ionic resin in the same pressure vessel, or we can use EDI, electrodeionization. A very popular technology right now utilizing the electricity to drive the ion exchange process. Degasification. Most often degasification is a decarbonator to reduce CO2. That's going to increase the runtime and performance of both our EDI and our mixed bed ion exchange. Or we could use gasification process to reduce all the gases that can be harmful downstream. So here are the technologies. We're pretty much very familiar with forced draft and vacuum degasification. A new one, just I want to say within the last 4 or 5 years, maybe not quite that much, is membrane degasification. It's a hollow fiber technology where the membrane itself is composed of a hydrophobic, hydrophobic meaning repels water, so it doesn't allow water to pass through the membrane, but it does allow the gases to pass through. So you can use membrane degasification technologies. And those, like I said, are becoming more prevalent. We move into deaeration. Now we're moving closer and closer to that boiler, that high pressure boiler. This is the reason you want to deaerate a boiler feed water. You can have severe oxygen pitting. It's not a very uniform pitting, corrosion. It's a pit, so it happens relatively quickly, and especially in the boiler tubes. And you can see on the left, this boiler tube's been cleaned. On the right, this one hasn't, so you can see the tubercles of the iron oxide that's being eaten by the oxygen and covering the pit. So this is severe oxygen pitting. So there's two ways we can deaerate a water source going to a boiler, mechanical and chemical. Mechanical is pretty simple. We're going to use feed water tanks or deaerators, and obviously the higher the pressure of the boiler, we're going to be moving into deaerators as opposed to feed water tanks. But it uses the solubility principles of temperature. The higher the temperature, the lower the solubility of any gas is in that liquid. And if we mix the water, the feed water, and steam to increase that that temperature of feed water very good, we're going to drive those gases off more efficiently. And like I said, we're going to move into deaerators when we get into the higher pressure boilers. And for that matter, anything over low pressure, probably anything over 150 to 200 psi is going to be using a deaerator as opposed to a feed water tank. Chemically, deaerators, even in a high pressure situation, are only going to take the dissolved oxygen levels down to about 7 parts per billion. That's too much to send to a boiler, so we still need chemical deaeration. And the oxygen, these scavengers we're talking about are in the lower pressure boilers, typically below 600 psi. You might see it as high as 900 psi. A sulfite donor such as sodium sulfite. Hydrazine is a real good oxygen scavenger used in the higher pressure boilers. Carbohydrazide, hydroquinone, DHA, MECO, and erythorbic acid. In the erythorbic acid, we're including things like ascorbic acid, vitamin C, but these are the oxygen scavengers that are used. Typically in the higher pressure boilers, you're going to be looking at the volatile amines, the hydrazine, carbohydrazide, and hydroquinones, DHA. We'll talk about hydrazine again in a minute when we get to all volatile water treatment programs, which we're going to talk about in just a second. So once we've deaerated the water, we need to talk about internal boiler water treatment. And the importance of the pressure of the boiler, once again, is the higher that pressure, the better quality feed water we need going to that boiler. Now, we're going to talk about several different treatment philosophies, but you can always treat a lower pressure boiler with the treatment recommendations for higher pressure boilers. You can't do the opposite. You can't treat a higher pressure boiler with treatment recommendations that are appropriate for lower pressure boilers. So we need to talk about the water quality guidelines. There are two societies, if you want to call them that have generated boiler water guidelines. One of them is the American Society of Mechanical Engineers, ASME. The other one that's used a lot in the electric power industry is EPRI. But both of these have guidelines for both feed water and boiler water. And here is an example of the ASME guidelines, and you can see, starting from the left, if you start moving toward the right on the top row, it shows you the higher the pressure, and then if you move down, you can see the recommendations for the boiler feed water and the boiler water. So let's take silica, for example, 0 to 300 psi boiler. We can have about 150 ppm of silica in the boiler. Not the feed water, in the boiler water. But as we increase in pressure, 301 to 450, we're down to less than 90. Up to 600, we're down to 40. Up to 700 psi, now we're down to less than 30. Let's go all the way up to 1500 to 2000 psi. We're less than 1 ppm of silica in the boiler water. So you can see, the higher the pressure of the boiler, the lower the feed water contaminants in the feed water and in the boiler after it's cycled up or concentrated up. So these are the guidelines that are used in the industry, predominantly for boiler water. Between these and EPRI is what most treatment guidelines are aligned with. So for boiler water treatment, I doubt you're ever going to see a carbonate cycle program in a high pressure situation in a power plant, but you can't talk about internal boiler water treatment without talking about carbonate cycle, so I've included it. Carbonate cycle has been replaced with precipitating phosphate programs where we feed a phosphate donor that will precipitate the calcium or the hardness as a hydroxyapatite, which is a real soft, fluffy sludge that we're going to blow out with the bottom blow down. Now we're moving into higher pressure boilers. Precipitating phosphate, you might see it up to 900 psi, but it's pretty limited to below 600 psi. I didn't mention on carbonate cycle, those are very low pressure boilers, probably even lower than 100 psi. Chelate polymer programs, once again, limited to about 600 psi. You might see them up into the 900s once in a while. All polymer programs. Then we get into the coordinated phosphate, which a lot of the high pressure boilers, and by high pressure I'm talking about over 1200 psi, maybe even up to a couple of thousand psi. Coordinated phosphate is using phosphate precipitation, but it's balancing the sodium and the phosphate ratios in the boiler depending on the pH. So there's basically two things you test for and monitor in a coordinated phosphate program. It's your pH and your phosphate levels. There are some treatment programs that are combinations or extensions of the coordinated phosphate program called congruent phosphate or equilibrium phosphate programs, but they're still phosphate, basically precipitation programs, just very low phosphate levels. And then we get into the very high pressure boilers with the all volatile water treatment. All volatile normally, typically, maybe even always, only uses ammonia for pH adjustment of the feed water, boiler water, and condensate, and hydrazine for passivation of the metal, boiler metal and condensate metal. Speaking of condensate treatment, there's a reason we need condensate treatment. It's because of CO2. Where does CO2 come from? It's basically the breakdown of the alkalinity in the feed water. Remember that carbonate alkalinity cycle I was talking about earlier? CO2 at the lower pHs, bicarbonate at the middle pHs, and carbonate at the higher pHs. Well, that alkalinity in the boiler feed water, under boiler water situations, flashes the CO2 into the steam. And then once it's in the steam, as the steam condenses, the liquid water again, condensate, reacts with the CO2 to form carbonic acid, which is obviously very acidic and can cause corrosion in the condensate system. Can also get it from contamination of condensate in plate and frame or in shell and tube heat exchangers. We could have the oxygen intrusion. Might even have poorly deaerated feed water or air intrusion into the concentrate. And the combination of those two, CO2 and water and oxygen, is much worse than one or two alone. So we need condensate corrosion inhibitors. We can feed a volatile neutralizing amines, filming amines, or oxygen scavengers as condensate corrosion inhibitors. The volatilizing neutralizing amines would be things like morpholine, cyclohexylamine, ammonia. But what they do is they neutralize that carbonic acid. As opposed to filming amines, they form a protective film on the surface of the condensate pipes to protect them. And then oxygen scavengers in case there is oxygen intrusion. So that's the typical modes for corrosion inhibitors for concentrate. So for more details on everything we've talked about, power generation water treatment. We have 2 3-day seminars coming up, one in January in Venice, Florida. I'm very proud to say that I will be co-presenting with David Paul at this one. So I'm going to learn a lot from David. That'll be a fun one. Both of us will be presenting in Venice, and then I will turn around and do the same training program by myself in Oceanside, California in February. So if you're interested in attending, please register on our website at dhptraining.com. And I want to thank you for attending and listening to me this afternoon. And what I want to do now is open it up to questions and answers. Okay, I see a first question here. It says, how can HERO play a role in improving water performance quality? I'm assuming you're talking about a HERO RO unit. HERO RO units take advantage of the silica solubility. In other words, remember I mentioned sulfonine or some other technology to take out all the hardness ions. If you take out all the hardness ions, you can't have that type of scale, meaning calcium, barium, strontium. You can't have a hardness scale. The only kind of scale you can have is a silica scale. So a HERO RO system takes advantage of that by the fact that if you get all the hardness out, You can raise the pH of the feed water up in close to 10 going to the RO unit. At a pH of 10, silica is much, much more soluble. So if silica is your only problem, HERO system is very advantageous. I think the original patent used coal lime softening to get all the hardness out of the feed water. Once the hardness is out, like I said, you can't have that kind of scale, so then you can raise the pH up extremely high to increase the solubility of silica, which is the only other kind of scale you can have. That's the HERO system. Next question. Okay, the question is, vapor line corrosion inhibitors the same as boiler scale inhibitors? Vapor line corrosion inhibitors are usually the amines that are fed that flash with the steam to protect the corrosion in the condensate lines. And yes, some of them will passivate the boiler, like DHA. But boiler scale inhibitors are typically, when you refer to a boiler scale inhibitor, it's typically either a polymer or a phosphonate or that orthophosphate I was talking about to make the calcium precipitated calcium hydroxyapatite, which is a fluffy sludge, as opposed to calcium carbonate, which is a hard scaling type sludge. Third question, back to the HERO system. Not only that, the high pH will greatly improve rejection of any, very true, yes. What the high pH does is it changes the form of boron, and at the higher pHs, that form of boron is rejected better by the RO system. So yes, good point. Next question, does the ASME or DHP recommend a specific type of RO membrane for boiler feed applications? No, they don't. ASME is just for boiler water guidelines, whether it's feed water or boiler, and DHP being a independent, non-biased consultant, we can't make recommendations of that type. So sorry, I can't help you there. Next question. Hello, what do you mean preventing chemical attack by UV light? UV light will destruct chlorine. There is a chlorine destruct. But like I said, it takes a lot of intensity, meaning a lot of energy, and there are easier ways to dechlorinate than using UV light. Now, having said that, I might have just upset some UV light manufacturers, but yes, UV light can be used for chlorine destruction. Okay, next question. Do you think that pH around 8.5 could reduce biofouling in RO units? Wow. You know, I'm not going to give an opinion there. Let me do some research for you. I'll find out who asked this question, and I'll better answer that after I do a little bit of research for you, okay? Okay, next question. What is the preferred pretreatment method for RO systems, sand filters or cartridge filters or others? Well, that goes back to your feed water source, and actually as important as that is the particle size distribution of the stuff in your feed water. Like I said, sand filters and multimedia filters can filter down to around 10 to 15 microns. Cartridge filters, typically 5 microns, maybe all the way down into 1 micron. But the important factor here is you would need a particle size distribution. In other words, that tells you most of your particles are 10 microns or above. X% of them is between 5 and 10 microns. X% of them is between 1 and 5 microns. X% of them is below 1 microns. That helps you determine what type of filtration you need in front of your RO unit. Got another question here. We had almost total plugging of the final membrane elements in the first pass. Second stage of a 2-pass RO unit, once due to some kind of clay I can't pronounce, Montmorillonite clay. So let's say clay. Apparently contained in the feed water that was below our ability to filter. Complete analysis of the TSS in the feed water could have prevented. I'm going to have to think about that question, but yeah, like I said, if you had a particle size distribution of these suspended solids in your feed water, you might have a better idea of how to prevent that type of fouling. I can only imagine that you had a lot of colloids going into your RO unit, colloids being less than 1 micron, and as they passed down the membrane unit, just like everything else in the water, they started coagulating or concentrating, which turned into coagulation and fouled those last units, those elements. So yeah, particle size would probably help you there. Okay, next question. Cycle of concentration for chloride is measured to decide boiler blowdown. So does different boiler water treatment will affect the boiler blowdown frequency? Yes, especially the carbonate cycle and the phosphate cycle. If you're using both of those phosphate precipitation programs, you're going to have more blowdown because you're actually precipitating stuff. The chelate polymer and all polymer programs don't require as much blowdown because they are solubilization programs where you're solubilizing things as opposed to precipitating them. But yes, it's very common for people to use chlorides to determine cycles of concentration in a boiler. Okay, here's another question. From the last question before, we think the clay from the 5+ SDI surface water went away when we switched to low SDI well water. Well, I would expect that. The SDI test is a 0.45 micron test, and if you had over a 5 SDI number once you did your calculation, number one, you voided the warranty of your membranes. Number two, that feed water is not acceptable to feed to an RO unit. So by switching to a lower SDI number, absolutely, your fouling rate is going to go down because the SDI number predicts the fouling tendency of the RO unit. Okay, I think okay, that was the last question. So if anybody else has any other questions, when you get your PDF that will be emailed to you probably in the next day or so, please forward us the question and I'll try to address it via email. Thank you for your attendance, and I will talk to each of you later. Goodbye.